Okay, let's look at this next portion here, which is about acceleration. Again, finally, we're getting into what is a reason that we would care about the second derivative. Well, one of the examples would be acceleration. It says earlier we saw that the derivative of a position function is the velocity function. Now we see that the second derivative of the position function, which is the derivative of the velocity function, is the acceleration function. So this is what we want to know right here. And here's the way that I look at it. You have s of t, and then you have v of t, which is s prime of t. The velocity is the derivative of the position function. Then you have a of t, which is the acceleration function, is the derivative of the velocity function, which is the second derivative of the position function. So this is really how I remember it, and I realize the connection between all those functions. Okay, so let's see here. It says a ball is thrown upward from on top of an 80-foot cliff. Remember, that would be your initial position, s sub 0, with an initial velocity of 64 feet per second. Remember, that would be v sub 0. It says the position function, s of t, equals negative 16t squared plus 64t plus 80, where t is measured in seconds. Again, that is correct because we know that s of t always has to be negative 16t squared plus your initial velocity times t plus your initial position. And all we're doing is plugging in that initial position of 80 feet high, and we're also plugging in that initial velocity of 64 feet per second. Of course, that's going upwards because it's positive. It says, so that does mean that our position function is the correct function here. It says find the height, velocity, and acceleration of the ball 2 seconds after it's released. So it wants us to plug in t equals 2 to the position function, which would be the height, to the derivative of the position function, which would be the velocity, and to the second derivative of the position function, which would be the acceleration. So let's look at these individually. Let's start off with, let's find the height of the ball after 2 seconds. So take the position function, which is negative 16t squared plus 64t plus 80. And all we want to do is look at it at t equals 2. So s of 2 would be negative 16 times 2 squared plus 64 times 2 plus 80. Plug that into your calculator now and let's see what you get. I'm plugging in negative 16 times 2 squared plus 64 times 2 plus 80. And in my calculator, I'm getting 144. Now notice this is a position function, so this is the height of the ball. So what was the height of the ball after 2 seconds? It was 144 feet in the air. Let's move on to the next. Let's find the velocity. The velocity function is the derivative of the position function. So let's find that velocity function. We need to take the derivative of negative 16t squared plus 64t plus 80. The derivative of negative 16t squared would be negative 16 times the derivative of t squared. The derivative of t squared is 2t, so negative 16 times 2t would be negative 32t. Plus 64 times t, the derivative of that is 64 times the derivative of t, which is 1, and 64 times 1 is just 64, plus the derivative of 80, and the derivative of 80 is 0, so I'm not going to include that. So our velocity function is negative 32t plus 64. Well, we can care about it at t equals 2. So v of 2 would be equal to negative 32 times 2 plus 64. Plug that into your calculator and see what you get, and I'm getting 0. Now remember, this is velocity, and velocity is measured in feet per second. We found the derivative of the position, measured in feet, with respect to time per second. So you're dividing by seconds there. Let's go ahead now and find the acceleration function. Well, that's the derivative of the velocity function, which is the second derivative of the position function. So find the derivative of what we got. Well, what's the derivative of negative 32t plus 64? Well, the derivative of negative 32t is negative 32 times the derivative of t. The derivative of t is just 1, and negative 32 times 1 is negative 32. And then the derivative of 64 is just 0. So the acceleration of t, regardless of the value of t, is always negative 32. So at t equals 2, it's still a of 2 is still negative 32. So there's my acceleration of the object. How is that measured? Well, it's with respect to the distance measured in feet, the derivative of the position function, which is measured in feet, with respect to time, seconds, with respect to time again, because we did the derivative twice. So this is per second per second. So that is your unit of measurement for velocity, for acceleration is feet per second per second. Okay? That negative 32, notice it didn't matter at what point in time. What that means is our acceleration is always constant. And on Earth, that's true if you're talking about an object moving downwards. It is always moving downwards towards the center of Earth, because that's where the pull of gravity comes from, at a rate of negative 32 feet per second per second. You'll also learn that in a physics class, I'm sure. So it says, in the previous example, we should notice that the acceleration of the ball is negative 32 feet per second squared at any time t. This constant acceleration is due to the gravitational force of Earth and is called the acceleration due to gravity. Note that the negative value indicates that the ball is being pulled down towards the Earth, or moving in a downward direction towards the ground.